Hello, good afternoon everyone, good afternoon every student who are here to join this session. Okay, so basically my name is Akshay, I'm from IIT Kharagpur, graduated with Mechanical Engineering as a BTech plus MTech degree. Okay, and I'm associated with Ask IITian as a chemistry faculty from last 2 years. Okay, today we are here to discuss about some basic part of organic chemistry, and that is normally guys having a problem in sir, how can we change 3D into Fischer projection? Normally do guys having a problem. Okay, so even my students is also having a problem that sir, how can we change 3D into Fischer projection, because 3D is 3D and they can't see 3D into a Fischer projection. So we have two methods, but because of the one method is very very typical to see that okay, we can change 3D into Fischer projection. So I'm giving you a very easy method that describes you that how can you change 3D into Fischer projection. Okay, let's take an example and then we decide how can we change it. Okay, so if I'm going to say that this is basically for making a 3D I need a chiral carbon, right, obviously. So I'm having a chiral carbon, and that is basically I'm having a plane. Let's say I'm having over here that is CS3, right, and I can say that okay, this is in the same plane. So if I'm having over here, I'm having an H over here, right? So let's say Br over here, okay, Br over here, and at the wedge position, this is my wedge position, right? This is a wedge position. At the wedge position, I'm having, let's say, H, and at the dash position, dash is basically to represent the bond that is going inside the plane, and the wedge position, wedge bond is basically to represent the bond that coming outside the plane. Okay, so this is where I'm having C2H5. Okay, let's say I'm having only one chiral carbon, and then we move on to the another chiral carbon. Then we're going to take two chiral carbon atom within a single compound. Okay, so first let's describe. Okay, to define the Fischer projection of this particular compound, let's first define the R and S configuration. First define the optical isomers, that what is it? Basically it's a R or S. Okay, so I'm marking the name for this particular compound, that okay, how we gonna define the position. Okay, so first Br is in the first position, you already know, because Br is very much above all of these compounds. Then second we have C2H5, right? And at the third position, I'm having CS3. So this is basically I'm defining the priority order. Okay. And at the fourth position, I'm having over here is H. Right. So my fourth is on the wedge position. And if you look at my previous video, that I told you that if my fourth number position or fourth number, position is basically on the wedge position, then we have to take the rotation from 3 to 2 to 1. Right. So we to take the rotation from 3 to 2 to 1. So this is basically going my rotation. Okay, and if you look at this rotation, basically this is what, anti-clockwise or clockwise? This is basically gives you anti-clockwise rotation, right? If I'm saying, so which one of the basically optical isomer shows ACW, that is anti-clockwise rotation. Anti-clockwise rotation, according to this S is move in the anti-clockwise direction, so this is for the anti-clockwise, and R, the shape of R, if you drawing the shape of R, that is basically for the clockwise. So obviously this is my S configuration, right? If you define this S configuration, fine, now you know this is basically for the S configuration. So now this is the right time to define the Fischer projection. Okay, now if I'm going to define the Fischer projection, first I have to take C, that is basically my chiral carbon atom. Okay, I'm taking C as over here, right? And then just mark it over here that one bond is over here, one bond is over here, and over here. So these are the 4 bonds we can mark for the carbon, because that is the maximum bond he can form, right? So now after defining these bonds, let's just place anything anywhere. Okay, you don't have to worry about Br I have to put on which position. Okay, let's just define it. Okay, just put Br over here arbitrarily. You need to put arbitrarily. Okay, just mind me, arbitrarily. Okay, let's say Br over here. I'm defining Br over here. Let's say CS3 over here. Fine, I'm defining CS3 over here. Okay, can we take H on this position? Let's take H on this position. Okay, this position is over here, I'm H. Remaining left is C2H5, so I'm going to represent C2H5 is over here. So I am defining this position. If you look at this, I'm defining arbitrarily. I don't take any rules or regulation over here to define the Fischer projection. I just define these position arbitrarily. That's it. Okay, I just place those substitute arbitrarily, right? Now this is my chiral carbon atom. Now place the numbering. Br we have to take in the first numbering. Okay. After that I have to take C2H5, right? And then the position for CS3 is 3, right? And the H is 4. And we always know that if you define the Fischer projection, that means you always know that, okay, if my bond is on vertical position, that means they are going inside the plane. They are some about like a dash bond, okay? And whichever bond I used to put in a horizontal position, they are basically look like they are coming outside the plane. So they are the wedge formation. So remember always this structure, that for the Fischer projection, whatever the bond come in the vertical position, they are going inside the plane. And whatever bond coming outside the plane, that is represented in the horizontal position. Okay? So you need to remember this one. Okay? Now, already we numbered it, right? Chalo numbering kar di. Ab then uske baad rotation. What remaining left? Rotation. Fine. So let's just rotate this one. So H basically comes in the dash position, right? If you look at this one, H comes in the vertical. And vertical, that means a dash position. And for the dash, I already told you, you have to take the rotation from 1 to 2 to 3. Okay, let's just take a rotation from 1. Okay, here I am having 3 over here. First I meet 3, so I have to take the rotation in this side, right? And if you take the rotation on this side, what I get is basically R, right? So this Fischer projection give me R, right? So we need to take care of this side, because in the 3D I am having S configuration, okay? But when we write the Fischer projection, I am getting R. So this is basically, that is how you understood, okay fine, this is not the correct Fischer projection for this particular compound which I represent in 3D. So you need to change the place of a substitute. Okay, how can you change the place of the substitute? Basically H, you have to remain left, H in this position, in the dash position. Okay, I have to remain left that H over here, and I have to change other C2H5 or CS3 or BR here. I have to change the position of either CS3, either BR or either C2H5. Now for this one I can say that fine, if I am going to take this side over here BR, if I am going to change the position BR over here and C2H5 over here, can I get the same configuration? Look at this one. Okay, now define the position and tell me if that one is giving you basically the same configuration or not. If you represent the line. Okay, now 3, 2, and this is basically, so this is over here, I'm having 1. So if I'm defining the rotation, I have to take 1, 2, 3, right? Because H in the vertical position, and that means in the dash. So I'm taking over here is 1, 2 and 3, right? And this gives me basically R, not R. This gives me basically anti-clockwise rotation, that is for the S. So now you can say that okay, my 3D and my Fischer projection gives me the same configuration. So this is the correct representation for this 3D compound. Okay, so this is the perfect Fischer projection for this 3D compound. Okay, now you understood okay, so you need to take care only one thing. You just need to, whenever 3D is there, you just need to define the configuration, whether it is R or S. Okay, after defining that, okay, it comes as, fine, let's just draw the Fischer projection arbitrarily. Okay, no need to worry about that. You draw the Fischer projection arbitrarily like I did do. Okay, I did that when I'm taking BR over here and C2H5, and it gives me R configuration, right? So I'm getting it that okay, if this Fischer projection give me R configuration and 3D giving me S, that means there is something wrong in my Fischer projection, right? So you need to change the position of the substitute, and that is how you're gonna change the position. Okay, so there is let's take one more example, because this is just for the one chiral carbon atom. Let's take two chiral carbon atom in a same compound. Okay. Let's say if I'm having C over here, that is basically my chiral carbon, and I'm having CHO over here, and this is basically I'm having Br over here, and this is where I'm having, okay, fine. So this is where I'm having this compound, right? So I'm having H over here, and this is where I'm having this thing, right? So you need to define, basically if I'm taking CS3 over here, now you need to define the Fischer projection of this particular compound, right? So let's take one more chiral carbon atom, and we are taking this also. So if I'm going to say that this is basically the plane that is outside the paper, and I'm taking Cl over here, and this is basically going inside the paper, and at that particular I'm having H over here, and I am taking the one more, let's say Br over here. Can I take Br? Okay, fine. Let's take Br over here. Okay. Now you have two chiral carbon atoms, so now you need to define the Fischer projection of this particular compound. Okay. How are you gonna define? First, same thing. You need to first you need to define the configuration. Okay. Just define the configuration. For that you need to place the position for that. Okay. CHO. I'm taking CHO as the first one because that is C and directly attached with O, right? And there is over here C that is directly attached to Br. Which one is greater one? O or Br? Br1. So this is gonna be my first position. This is gonna be my second one, right? And this is directly attached with 2O. This is attached with Br and Cl. Both is greater. So this is obviously my first. This is my second. This is my third, and this is my fourth, right? Now for this one, my H, my fourth position is on the dash line, right? So I have to take the rotation 1, 2 and 3. So I'm going to take this rotation 1, 2 and 3, and that gives me anti-clockwise. That means it's a S configuration. Now look at this one chiral carbon atom, and for this one I'm having Br over here. That is my first, that is my second, and that is my third, and this is my fourth. So 4 again is on the dash position, right? So we need to take the rotation 1, 2 and 3. So this is my rotation, and this is basically again give me what? S configuration. Now you need to define the Fischer projection, and how you're gonna do that I already told you. You just need to draw a line, simple line C, and over here C, there is basically this one, and that is basically this one, right? Now you need to define that so that it will gives you basically S configuration, both S configuration. Both chiral carbon basically having a configuration of S, right? So you need to take care of that, and by that you can define the Fischer projection. Let's say I'm just putting the compounds, the substitute arbitrarily. Let's take this carbon, and what are the substitutes? CHO. Let's say CHO over here. I'm having CHO over here. Fine. Let's take CS3 over here. CS3, and I'm taking H over here, and this whole compound I'm taking in the downside, right? Now come to this chiral carbon, the second chiral carbon, and we need to define Cl over here, okay, H over here and Br over here. I'm just arbitrarily put that, right? I don't follow any rules and regulation, I just put arbitrarily. Now let's take the care of basically the R and S configuration. So first define, if you define this particular carbon, for this particular carbon I'm having first position over here, second for this one, third for this one, and fourth for this one, right? Now according to this, 4 is on the wedge position. If you look at this one, simpler one, 4th is on the wedge position. Now if 4th is on the wedge position, you have to take the rotation from 3 to 2 to 1. If you take 3 to 1 configuration, that will gives you what? Anti-clockwise. If it is anti-clockwise, that means it gives you S. That means for first carbon, I'm having the same configuration. That means this is the correct representation for first carbon. Now let's take care of the second carbon also. Same thing. Let's define. This is I'm having Br, 2 over here, 3 for this one, and 4 for this one. Now my fourth position again is on the wedge side, so I have to take care. So basically I need to take the rotation from 3 to 2 to 1. Now this is basically gives you clockwise rotation. That means it gives you R. That means there is something wrong in this particular Fischer one. For the second one, I'm doing something wrong. Okay, so you need to take care of that and change the position. Now, what is the process? Just change the position of a substitute. That's it. Okay. Now, basically, you want clockwise rotation, and how you get clockwise rotation? By basically you have to stay this H over here. You have to take place this H over here because of this. Okay, and if H is on the wedge position, you need to take the rotation from 3 to 2 to 1. Okay, and how you gonna do that? If your second position comes over here, you will get 3 to 1 position, and that becomes S, right? So which one is my second one? Second over here I am having Cl. So just put Cl over here, so that you can get the S rotation, the anti-clockwise rotation. Now if you look at this compound, basically it gives you what? S rotation. So that becomes S configuration. So earlier I am getting R for the second carbon, but now I am getting S by just changing the position of the substitute. Now that is how you gonna change the 3D into Fischer projection. So that is I think that is the very simplest thing you can do for changing the 3D into Fischer projection. You need not to worry about what is the rule for that and what is the regulation for that. You just take care of first define the configuration, whether it is R or S. Fine. Let's just do basically you draw the vertical or the horizontal line. Fine. Now after that you just need to put the substitute arbitrarily. If you put the substitute arbitrarily, then you have to take care of the configuration. If your configuration is right, though whatever we have in the 3D, that is good. If you don't get that particular rotation, that means there is something wrong and you need to change the position of a substitute. That's it. That is the only thing you have to do to get your Fischer projection from 3D, and I hope that is the simplest thing, so you can do it. So thank you very much to have this session, and in the next time I will give you some interesting topic also for the organic chemistry. So thank you very much.